Hello everyone, this is Dr. Bharat from Global Academy of Technology. In my last video session, we had discussed about analyzing the trusses with two elements. In this session, we will be analyzing the truss structures with three elements. During the process, we will be determining the displacements, reactions and stress in the structures. Let us have a very quick overview about the truss members. A truss is a two force members. Basically, they are the combination of bar elements. It can take either tensor loads or compressive loads. A truss element will have 4 degrees of freedom, 2 at each node. The stiffness matrix is represented by the equation shown on the screen. In this equation, E is the Young's modulus, A is the cross-sectional area, L is the length of the truss element, and L and M are the directional cosines. The reactions of a truss element are determined by the equation R is equal to KQ minus F. The strain can be calculated by multiplying the strain displacement matrix with the displacement vectors. The strain displacement matrix is given by the equation 1 by L multiplied by the directional cosine matrix, and the stress can be obtained by multiplying the strain with Young's modulus. So with the previous basics, let us now start analyzing the trusses with three elements. Clearly observe the structure. This structure is a truss element having three elements. We need to determine the displacement at each node, the reactions and stress for the structure. Also, the Young's modulus and area of the structure is given in the example. For any problem to begin with in finite element analysis, first the problem has to be converted into FEA model, which consists of nodes and elements. The FE model of this element is shown here. It consists of totally three elements, 1, 2 and 3, and also 3 nodes. Element 1 is in between node 1 and node 2. Element 2 is in between node 2 and node 3, and similarly element 3 is between node 3 and node 1. Also observe here, the triangle given is an equilateral triangle. So all the sides will be having the same length of 1 meter each. The total degrees of freedom for the entire structure is 6. That is, the structure has got 2 degrees of freedom at node 1, Q1 and Q2, 2 degrees of freedom at node 2, Q3 and Q4, 2 degrees of freedom at node 3, Q5 and Q6. Also, to start with, the origin is required to find the nodal locations. The origin is considered at node 1. So, the coordinates of first node is 0, 0. The coordinates of second node will be 1000, 0. In order to find the coordinates of third node, we need to do a small mathematical geometrical calculation. Let us consider drop a straight line from the center so that we will make use of this right angle triangle to determine the distance. The adjacent side will be equal to 500 mm because the total length of the element is 1000 mm and it is a equilateral triangle. The opposite side can be calculated by applying tan 60. Tan 60 is equal to opposite by adjacent. Therefore, by multiplying tan 60 with 500, we will be able to determine the opposite side. Therefore, the x-coordinate of node number 3 is 500 and the y-coordinate of node number 3 is 866.02 mm. Note that the units in meters are converted into mm. Always it is preferred to use a common set of units. The next stage is to determine the lengths of the elements. Since it is an equilateral triangle, all the lengths will be the same. Later, let us start filling the element connectivity table, which consists of the element, the starting node, final node, element length as well as directional cosines. For the first element, as shown in the figure, the starting node is node 1 and the end node is node 2. Therefore, the element 1 is in between the following displacements Q1, Q2, Q3 and Q4. Similarly, the node 2 is in between node 2 as well as node 3. The starting node for element 2 is node 2 and the end node is node 3. And hence, node 2 is in between the following displacements Q3, Q4, Q5 and Q6. Clearly observe the element number 3. It is in between the two nodes 3 and 1. Therefore, for element 3, the starting node is considered as 3 because we will be following a cyclic process. Therefore, the starting node of node 3 will be, for element 3 will be node 3 and the end node is node 1. Therefore, node 3 will be in between the following displacements Q5, Q6, later Q1 and Q2. With this basics, let us now start finding the directional cosines. To find the directional cosines, the node locations are most important. These are the equations which are used to find the directional cosines. In this case, x final represents the x coordinate of the end node of a particular element and x start represents the x coordinate of the starting node of an element. Similarly, m represents the y coordinates. Let us now start finding the directional cosines for element number 1. For element number 1, L is equal to 1000 minus 0. Here, the final node of element number 1 is node number 2 and the corresponding x coordinate is 1000. And the starting node of element number 1 is node 1 and the corresponding x coordinate is 0. Thus, we have got the value of L is equal to 1000 minus 0 divided by the length of the element. Similarly, to find the value of M, the y coordinate of the end node of element number 1 is 2 and its y coordinate is 0. Similarly, the starting node of element number 1 is node 1 whose y coordinate value is 0. Thus, the value of M is 0 minus 0 divided by 1000. Let us now find the directional cosines for element number 2. The element number 2 is in between node 2 and node 3. The starting node is taken as node 2 and the end node is taken as node number 3. To find the directional cosines, the value of L takes the value of x coordinates. Here 500 is the value of node number 3, which is the final node of element number 2. Similarly, the starting node of element number 2 whose x coordinate value is 1000. Thus, we have got the value of 500 minus 1000 divided by the length of the element. In order to find the value of M, once again the final node y coordinate value minus the starting node y coordinate value will give the value of M. Now for element number 3, one need to be careful here because element number 3, the starting node of element number 3 is node number 3 and the end node of element number 3 is node number 1. Therefore, we should be careful while calculating the directional cosines for element number 3. Here, the x-coordinate of the final node is 0, thus it has been 0 here, and the x-coordinate of the starting node, that is node number 3, is 500. Thus, we have got the value of L as 0 minus 500 divided by the length of the element. Similarly, to find the value of M, the y-coordinate of the final node, that is nothing but 1, is 0, and the y-coordinate of the starting node, nothing but 3, is 866.02. By substituting these values in this M, we will be able to determine the value of the directional cosine for element number 3. These directional cosines are listed in element connectivity table. After determining the directional cosines, we will now try to determine the stiffness matrix. By substituting the given values in the numerical in the following equation, which is K is equal to EA by L multiplied by the directional cosine matrix, we will be able to determine the stiffness matrix of individual element. For an individual element, the stiffness matrix will be 4 cross 4 matrix because there will be only 4 degrees of freedom for each element. But for the entire structure, the number of degrees of freedom are 6. Therefore, after assembling all the 3 stiffness matrices, the global stiffness matrix will be 6 cross 6. By substituting these values, we will be able to determine the stiffness matrix for element number 1, which is surrounded between the following displacement vectors Q1, Q2, Q3 and Q4. That is what it is represented in the diagram also. Now, the stiffness matrix for element number 2 is given by this following equation. The element number 2 is surrounded between Q3, Q4, Q5 and Q6, which is represented here. Similarly, element number 3, the stiffness matrix is shown here, which is surrounded by the equations or the displacement vectors Q5, Q6 and Q1 and Q2. Note that here it is Q5, Q6, Q1 and Q2. These notations are most important while assembling the stiffness matrices. Let us now understand how do we assemble this stiffness matrices to form the overall global stiffness matrix. Let us now understand how to assemble the elemental stiffness matrices to obtain the global stiffness matrix. Once again, I would like to remind you that the element number 1 is in between the 4 displacement vectors Q1, Q2, Q3 and Q4. The top one represents the columns of the matrix and the vectors on the right side represents the rows of the matrix. Similarly, the element 2 is in between the displacement vectors Q3, Q4, Q5 and Q6. The top one, as I said, they are the columns and the right side displacement vectors represent the rows of a matrix. Also, the matrix K3 or the element K3 is in between the following displacement vectors Q5, Q6, Q1 and Q2. The order of this displacement vectors plays a very much important role. The order cannot be Q1, Q2, Q5, Q6 because for element number 3, the starting node is node number 3, which has the displacement vectors as Q5 and Q6, and the end node for element number 3 is node number 1, which has got the displacement vectors as q1 and q2. So the matrix should be q5, q6, then q1 and q2. Let us now understand how do we assemble these matrices to form a global stiffness matrix. As usual, the first matrix is in between these vectors q1, q2, q3, q4, which goes in this area. Thus, q1, q2, q3, q4, these rows and columns are filled with the first stiffness matrix elements. The second stiffness matrix are placed in the respective columns and rows between q3, q4, q5 and q6, and similarly these are the rows which we have placed the stiffness matrix. Now let us start filling the elements of K3 in the global stiffness matrix. To begin with, let us start filling the empty rows and columns, that is Q5, Q6 and Q1 and Q2. This is the reason why we have divided the stiffness matrix into 4 equal parts. Let us search for the matrix which is available here. The rows must be Q1 and Q2 and the columns are represented by Q5 and Q6. Now here, if you can observe the blue color matrix here, Q5 and Q6 are the columns for this elements and Q1 and Q2 are the rows for this elements. So this values minus 5.25, minus 9.09, minus 9.09 and minus 15.75 should be belonging to this area. Thus, the matrix, the values will go here. Later, let us see how do we fill another empty row and column. This is in between the columns Q1, Q2 as well as the rows Q5 and Q6. This is represented by the orange color matrix in K3. Clearly observe, even this orange color matrix elements are between the columns Q1 and Q2 and the rows are Q5 and Q6. Thus, these elements are placed in this area. Now, let us start filling the other parts. Carefully observe here, the yellow color one, it is Q1, Q2, these are the rows and these are the columns. The columns and rows are represented by Q1 and Q2. Therefore, this yellow color one belongs to this area, Q1, Q2. Similarly, the green color one, which is in between these columns Q5, Q6 as well as Q5, Q6 rows, which happens to be in this area. Thus, the matrix has to be assembled. These values has to be added so that we will be able to determine the global stiffness matrix. Now, the values here are added. Here 21 belongs to the first element, first stiffness matrix, and plus 5.25 belongs to the orange color value in third stiffness element. Similarly, we start adding these elements. Thus, we will be able to determine the global stiffness matrix for the given truss structure. This will be the global stiffness matrix. The users must practice the assembly of stiffness matrices very carefully, and also one need to understand how do we number the elements and write these displacement vectors in exact order. Just like in case of element number 3, we need to carefully choose which is the starting node and which is the end node. Based on this only, we will be able to assemble the matrices to obtain global stiffness matrix. Let us now use this global stiffness matrix to determine the displacement vectors. The Golding equation in FEM is given by the formula KQ is equal to F. In this triangular element, since node 1 is hinged, there will be no displacement at node 1. Therefore, Q1 and Q2 values will be zeros. Similarly, there will be no displacement at node 2. Thus, the value of Q3 and Q4 will also be zeros. But since there is no support at node number 3, the values of Q5 and Q6 will remain. Thus, obviously, the major unknowns in this process is Q5 and Q6. Let us now see how we have got minus 80,000. At node number 1, there are no forces. So, first two elements in the force vector are zeros. At node number 2, also there is no force vectors, no loads. Therefore, F3 and F4 are also zeros. But when it comes to node number 3, there is a force in the direction opposite to Q6 and there is no force along Q5 direction. Therefore, F5 is 0, but there is a force in the direction opposite to Q6. Since it is opposite, we will be taking as minus 80,000. Once we have arrived with the proper values of displacement vectors as well as the force, now we will use the elimination approach to reduce this matrix. Since the displacement vectors are zeros, the corresponding rows and columns will be eliminated. In this case, row 1 and column 1, row 2, column 2, row 3, column 3, row 4 as well as column 4 will be eliminated. Thus, you will be able to get the displacement reduced stiffness matrix where you will be able to find the value of Q5 as well as the value of Q6. Once you have found the values of Q5 and Q6, the next stage is to determine the reactions. The reactions can be determined by using the following equation. R is equal to KQ minus F. So, one should be very good with matrix multiplication so that you will be able to do this multiplication carefully and obtain at the following values. The strain can be determined by multiplying the strain displacement matrix with the value Q, nothing but the displacement vector. There will be 3 strains which corresponds to each element. For element number 1, the strain is given by the following equation: 1 by L multiplied by the directional cosines multiplied by the displacement vector that corresponds to element number 1. Since the element number 1 is in between Q1, Q2, Q3, Q4, these are the values which has to be noted here. By substituting these values, we will be getting the strain in first element as 0. Since the force is only applied exactly at Q6, there is no strain in element number 1. For element number 2, the strain can be given as 1 by L2, where L2 is nothing but the length of the element multiplied by the directional cosines of element number 2, that is minus 0.5 and 0.866 multiplied by the displacement vector which corresponds to element number 2. Since the element number 2 is in between the following displacement vectors Q3, Q4, Q5 and Q6, the corresponding values of this displacements has to be placed here, and on carefully performing the matrix multiplication, we will be getting the value of strain as minus 0.0022. For element number 3, we will be getting the strain by multiplying the following equation with the displacement vectors. Element number 3 is in between the following displacements Q5, Q6, Q1 and Q2. Thus, the values of Q5, Q6, Q1 and Q2 has to be substituted here, and will be able to obtain the strain for element number 3. The stress in the entire structure can be determined by multiplying the Young's modulus with the strain. Since there are 3 elements, we will be getting the 3 different components of stress for element 1, element number 2 as well as element number 3. For element number 1, the stress will be 0 since the strain is also 0. For element number 2, the stress is minus 461.88 megapascals. And for element number 3, the stress is same as the previous, that is minus 461.88 megapascals. It is clearly observed from the structure that element number 3 as well as element number 2 are subjected to compressive loads. Thus, while performing the analysis of a truss with 3 elements, 2 most important steps is finding the directional cosines, and second most important step is to assemble the stiffness matrices. Care has to be taken while assembling, especially third stiffness matrix. Let us now solve one more example to understand this process. This example is pretty simple than the previous. Here the dimensions has been given clearly 1 meter, and in addition to the previous there are the roller supports. If you carefully observe, at node number 2 there is a load of 100 kilonewtons, and at node number 3 there is a load of 200 kilonewtons. Also the Young's modulus and the area in meters has been given in this numerical example. Even though the values are in meters, we will try to have a common notations where the entire values will be converted into millimeters. The first and foremost step in performing the analysis is to convert the given FE model into the corresponding nodes and elements. This structure has got 3 elements and 3 nodes. The entire structure has got 6 degrees of freedom. To begin with, let us find the nodal locations or the coordinates of each node. To find the coordinates, we should have an origin, and for this structure the origin is selected at node number 1. Thus, the nodal locations are pretty easy to determine here. For node 1, the location will be 0, 0. For node 2, the coordinates will be 1000, 0, and for node 3, the coordinates will be 0, 1000. Later, we need to find the lengths of the elements. Length of first element is clearly given as 1000 mm. Length of third element is also given as 1000 mm. To find the length of second element, we will be making use of Pythagoras theorem, which is pretty simple to use. Thus, the lengths of 3 elements are listed here. Once after finding the lengths, the next important step is to list the elements of element connectivity table. For the first element is in between the nodes 1 and 2. Thus, for element number 1, the starting node is node number 1 and the end node, final node, is node number 2. Similarly, for element number 2, the starting node is node number 2 and end node is node number 3. And for element number 3, the starting node is node number 3 and end node is node number 1. Always we need to follow a cyclic process in choosing the starting node as well as the final node. Let us now determine the directional cosines. Nodal locations plays a very important role in determining the directional cosines. These are the equations of directional cosines. By substituting the corresponding x coordinates of final as well as starting nodes of element number 1 in these equations, we will be getting the value of L and M for element number 1. Here 1000 corresponds to the x coordinate of final node of element number 2, that is 2. and 0 corresponds to the x coordinate of the starting node of element number 1, that is 0 in this case. Similarly, m corresponds to the y coordinates of starting and final nodes of element number 1. Also, for element number 2, we'll be considering the starting node, that is 2 and 3. If you take the x coordinates of node number 2 and node number 3, we'll be getting the value of L. Similarly, if you consider the y coordinates of node number 2 and node number 3, we'll be getting the value of M. Only here, the final node, the y coordinate of final node minus y coordinate of starting node divided by length gives the value of M. Similarly, the values of L and M can be obtained for element number 3. In this case, the starting node is node number 3 and end node is node number 1. Once we get the values of directional cosines, these values will be listed in element connectivity table. Once we have determined the values in element connectivity table, now we'll be determining the stiffness matrices. From the given values in the example and substituting these values in stiffness equation, we'll be able to determine the 3 stiffness matrices. Always understand that, as done in the previous example, the element number 1 is in between the values Q1, Q2, Q3, Q4. Element number 2 is in between Q3, Q4, Q5 and Q6, and element number 3 is in between the values Q5, Q6 and Q1 and Q2. Now we'll be using the same procedure which we have discussed a little earlier to assemble all these 3 individual element matrices to obtain overall global stiffness matrix. To begin with, the stiffness matrix K3 is divided into 4 parts, and we'll start filling these parts in this particular zones. Initially, the first zone Q1, Q2, Q3 and Q4 is filled by the first stiffness matrix. Later, the second zone, which is represented by Q3, Q4, Q5, Q6, will be filled by the second stiffness matrix. Here, whenever there is an overlap, it is understood that the values has to be added here. Similarly, let us now start filling the other zones which are represented by the stiffness matrix for element number 3. This blue color matrix elements will fit in this zone because it corresponds to the following columns Q5, Q6 as well as Q1 and Q2. Thus, these values will go and will be located in this zone. Similarly, the empty zone which is shown here are represented by Q1, Q2 as the columns and Q5 and Q6 are the corresponding rows. Thus, the yellow color matrix will be, thus the orange color matrix will be placed in this area. Now, the remaining matrices, matrix elements, that is green color one as well as yellow color one, will correspondingly occupy the other areas of these matrices. These values corresponds to the values of Q1, Q2, Q3, Q4, Q5. One needs to be very careful while performing the assembly process. Here this matrix is filled here, therefore obviously the other matrix will be filled in this zone. So thus, once again I repeat, whenever there is overlap, understand that the corresponding elements has to be added. Once we add these values, we will be able to obtain the overall global stiffness matrix. This will be the overall global stiffness matrix. Now we will be using this matrix to determine the unknown displacements. The unknown displacements can be determined by substituting the stiffness matrices in the governing equation. Thus, we will be having a governing equation as shown on the screen. By substituting the boundary conditions, we can start eliminating the corresponding rows and matrices in stiffness matrix. Now carefully observe that node number 1 is supported with hinge support, thus there will be no movement in x direction as well as in y direction. Thus Q1 and Q2 are zeros. When it comes to node number 2, there is a roller support. The roller support clearly indicates that this node can move in x direction and it cannot move in y direction. Thus, there will be a value of Q3 which will be available and Q4 will be 0. There will be no movement in y direction. Similarly, if you go at node number 3 has got roller support, which clearly represents that the node can move in y direction and not in x-axis. Thus, the value of Q5 will be 0 and the value of Q6 will need to be determined. By substituting these values, these boundary conditions, we will be able to determine the values of Q3 and Q6. Also, at node number 2, there is a load of 100 kilonewtons which is in the direction opposite to the value of Q3. Thus, the value is minus 10,000 newtons. Similarly, there is a load of 200 kilonewtons in the direction of Q6. Therefore, next to Q6, there is a force of F6 will be 20,000. Remaining all the places will be zeros because there is no loads acting at that particular areas. Now, by using elimination approach where the corresponding rows and columns will be eliminated, we will be able to determine the reduction matrix or reduced stiffness matrix, which can be carefully. The reactions can be determined by using the following equation. The strain of individual element can be determined by multiplying the strain displacement matrix with the load vectors. The strain for element number 1 will be minus 0.0002. For element number 2 is given, as well as the element number 3 can be calculated. There will be stress for each element and can be calculated by multiplying the strain with the corresponding Young's modulus. Thus, the strain for element number 1 is minus 12.07 megapascals. For element number 2 will be 2.93 megapascals, and for element number 3 it is 30 megapascals. Thus, the stresses with 3 elements can be analyzed. The viewers are requested to try out these numericals by yourself so that you can understand how the matrices can be assembled. Here you need to use this equation 60 degrees to find the length of the third element. Here in this numerical, the length of first element is given as 500 centimeters, second element is given as 800 centimeters, but the length of third element has not been given. Here 20 centimeter square and 10 centimeter square represents the areas of each element. So a careful geometric analysis will make you to find the values of the length of the third element. Now in this numerical, the load is inclined, so we need to resolve this load into a horizontal component and vertical component. While resolving the forces, you need to understand that the component, horizontal component, since it is next to the angle, it will be 80 cos 60 degrees. Similarly, the vertical component will be 80 sin 60 degrees. So try out with these examples. Thank you, my dear friends, for watching this video. A careful analysis of trusses will help you in determining or building a strong structures. We'll meet in the next video session. Have a nice day. Thank you.